thanks everybody for attending, and thanks Beret for accepting to participate in this webinar.
Thank you for inviting me.
It's a real pleasure for us to invite you here to give a talk. I think I don't remember exactly when we met last time. I think it was in the Global WordNet conference in Singapore a few years ago, before the pandemic. So it was very good. For everybody, thanks for coming. This is the second webinar this season. Is going to be presented by Shwartz from University of British Columbia, and she's going to give us a talk about common-sense reasoning, also in NLP. For us, it's a real pleasure to invite her, because I think she's a very bright and researcher on that topic, and she has been doing very nice work. So this is the second seminar. The first one was also about common sense reasoning by Jiang Ren. It was also very interesting. I think this is right now a real hot topic now in natural language processing, and I think this is also a very challenging thing. A few years ago, nobody was saying a word about common sense because it was so difficult, and now several people and very interesting researchers are paying attention now to knowledge, common sense knowledge, and also reasoning things. So that's why we also invited Beret, which is, I think, she's doing very nice work. She's going to talk about common sense reasoning into NLP. Beret is now an assistant professor in the computer science faculty in department, I don't know, at the University of British Columbia, and also faculty member of the Vector Institute for Artificial Intelligence. And she has been work a lot on common sense reasoning and semantics and pragmatics, and also on multi-word expressions, which also are very difficult to grasp and to understand fully. She has been also working on the Allen Institute for AI in the University of Washington, and she was a PhD student in Bar Ilan University with Ido Dagan there. So it's a real pleasure for us to invite her to give a talk. So I hope you enjoyed as well as we are going to do that. So at the end of the presentation, there will be a few minutes for questions. It could be also by voice, but also you can also use the chat if you prefer. So thank you, Beret, once more, and waiting for your presentation.
Yeah, thank you very much for the nice introduction and for inviting me. I'm hearing echo. I don't know if I should. Yeah, I think it's fine. So yeah, thank you very much for inviting me. Let me quickly share my screen. Okay, I'm assuming you can see the slide.
Yeah, we can see it, definitely.
Okay, great. So yeah, today I will be talking about incorporating common sense reasoning into NLP models. So I want to start with a little bit of background of why do we actually need common sense reasoning in NLP. So in the last decade, we've seen impressive progress on multiple NLP fronts, thanks to deep learning, and a few years ago, thanks to the new paradigm of pre-training and fine-tuning language models. And while we may be able to dismiss media reports about human-level performance on text understanding and generation, we pretty much get the same conclusion by looking at leaderboards such as Superglue, that even though they involve a range of complex language understanding tasks, yet models have already surpassed humans. And so, and the most recent success was in the last 4 years from pre-trained language models. So I'm assuming this is already common knowledge at this point, but just to be on the same page, such models like BERT are first pre-trained to read a large text corpus, such as Wikipedia or web text, and predict a missing word from its context. For example, parrots are masked birds. The model can predict something like intelligent. As a result of this pre-training, these models learn a lot about syntax, word meanings, factual knowledge, etc. And typically, you would then fine-tune these models with task-specific data and objective to perform a task such as, for example, sentiment analysis. So the way to do that would be to encode a text such as the chocolate cake is amazing, using the language model, getting some vector representation from the language model, feeding it into a classifier to predict positive or negative, and then the loss from the task back propagates to update both the classifier as well as BERT's weights. And this fine-tuning step is responsible basically for understanding and learning to solve the task. However, we do have a generalization issue. So while we're getting good at many tasks, we still have a way to go in solving both the harder tasks as well as the long tail of the easier tasks. And as long as we're training machine learning-based NLP models, they will only be trained on a sample of the situations that they may encounter during inference. So if we actually want them to behave reasonably when they encounter situations outside their training sample, we may provide them with the same tool that humans use, which is common sense reasoning. So a few reasons why NLP models need common sense because of different properties of language. So first of all, natural language is often ambiguous. So a headline, this was in the news a few years ago, Stevie Wonder announces he'll be having kidney surgery during London concert. So this headline has multiple interpretations. And if you actually feed this along with a question, when is the surgery, into unified QA, which at the time was state-of-the-art question answering system, it incorrectly answered during London concert because there's a very strong syntactic cue here. Well, we can easily determine that the announcement happened during the concert, but the surgery happened sometime later, based on our common sense knowledge that kidney surgery is likely performed under general anesthesia and that people are unconscious under general anesthesia, therefore unable to perform actions like singing or playing. A second property of language is that it's often underspecified. And so that's because we only say what we believe to be complementary to the listener's knowledge. And for example, sometimes you would have an expression that holds some kind of implicit meaning, as in this case, a translation system translating grass-fed yogurt to a language that doesn't have an equivalent phrase in the target language would need to actually make this phrase explicit. Here, Google Translate incorrectly translated grass-fed yogurt to Hebrew to the equivalent of yogurt with grass. What I would have not expected, but what I would have wanted it to say was something like yogurt made of milk from grass-fed cows. And the reason I know this is what it means is because I know that yogurt is typically made of milk. Cow milk is usually the default, otherwise it would be specified. And cows eat grass, while yogurt doesn't eat anything because it's an inanimate object. And finally, and crucially, language as a social function. So if you're developing a chatbot to give medical advice or mental health advice, you want it to have some kind of social norms and ethics to know better than advising patients to kill themselves. So I've been mentioning common sense for a few minutes now, but I didn't really define what it is. So it's pretty broad. The definition is pretty fuzzy, but I'm going to go with the definition that we used in the common sense tutorial we gave at ACL a few years ago. So that's the basic level of practical knowledge and reasoning concerning everyday situations and events that are commonly shared among most people. So that includes, for example, physical common sense, such as knowing that it's a bad idea to put your hand on top of a hot stove, social common sense, such as knowing that it's impolite to comment on someone's weight. Temporal common sense, such as eating dinner comes before going to bed, etc. In the last 5 years or so, once we've managed to achieve good performance on syntax and some semantic tasks in English specifically, there has been more work on pragmatics and common sense reasoning. To demonstrate that, on the right side, this is the number of papers about common sense in the ACL ontology with a pretty simple keyword search with common sense with or without space. So in 2020 and 2021, there were more than 60 papers each. On the left side, this is the number of papers in the ACL ontology in general. It's for the sake of fair comparison, but even though it's on a different scale, so I'm not sure the charts actually convey that message. But what I'm trying to say here is that the growth in papers about common sense is disproportional to the growth in papers in general. And then among the papers about common sense, again, using this kind of keyword search, many of them introduce a new benchmark or a model that solves this benchmark, or there's also an overlap, because usually when papers introduce a new data set, they also introduce a model to solve it. And there's less work on incorporating common sense knowledge or reasoning models to improve other NLP tasks. But it is getting more popular. So here are a few examples for using common sense for recognizing, interpreting, and generating figurative language. This is actually, I think, an older example of using common sense reasoning to improve machine translation and to better understand human needs and emotions, which is not a downstream task on its own, but could be then used in many downstream tasks. So in this talk, I will discuss some of our work in which we use common sense to improve NLP models. I'll start by talking about our work on using common sense to detect when two text mentions refer to the same event in the real world. Then I will present a task for interpreting figurative language in narratives, and a model that uses common sense and is also inspired by human strategies for interpreting figurative language. The last project I will discuss, if I have time, I'm not sure, will be an ongoing project about finding what knowledge is missing and completing it in the context of question answering. And then I will discuss some open problems and future directions. So let's start with event coreference. This is a project led by my student Sahitya in collaboration with Raymond at UBC and Chris Tanner, who was at Harvard, is now at MIT, and don't remember where else. And so this project is called What Happens Before and After, Multi-Event Common Sense in Event Coreference Resolution. So in coreference resolution, the goal is to cluster together mentions of the same entity, for example, Tara Reid and she, as well as the same events, for example, entered and checked into. And in cross-document coreference resolution, mentions of the same entity or the same event may appear in multiple documents. For example, the American Pie Star also refers to Tara Reid. This is an example from the ECB Plus dataset, which is commonly used for cross-document coreference resolution. The standard methods, at least in the last few years, the standard neural method works as follows. So first, possible mentions are extracted from the text. Then scorer is trained to predict the confidence that every pair of mentions refer to the same entity or the same event. And finally, agglomerative clustering is applied based on these scores to output clusters of events and clusters of entities. In this work, we focus on events like enter and check into, although in previous work, or me and other authors, showed that modeling events and entities jointly is helpful. So we may go back to that in the future. And the specific problem we addressed was difficult coreference problems where the two event mentions are not lexically similar, but given additional context or common sense reasoning, they may be inferred from each other. So here's one example. The first document says, the third coworker, Brian Dalton, 39, spent 2 weeks in the medical facility and still is recovering from gunshots to the neck and shoulder, prosecutor said. The second document says, Brian Dalton, 39, was shot in the neck and is hospitalized in good condition. So spent and hospitalized are not lexically similar in general, and they're not even substitutable in the same context. So for example, if you ask Bert for substitutes for spent in the first sentence, then it suggests served, survived, has, and had. And for hospitalized in the second sentence, it suggests still, now, currently, not, and considered. To resolve this reference, we actually need to infer that spending 2 weeks at a hospital or even spending more than a day at a hospital likely entails being hospitalized, as opposed to if you go there for a few hours, that might mean that you're just visiting someone or getting a checkup. So we can try to use the COMET model for this. COMET is a language model that was fine-tuned on the atomic knowledge base, and it can generate inferences about events, specifically about the prerequisites, the motivations of the participants, causes and effects, and more. So for example, for these two sentences, it tells us that Dalton is seen as sick and that he wants to be healthy. And there's a very high overlap between the inferences for the two sentences. They are identical in this slide, but in practice, it was a very high overlap. So that can really help the system resolve the coreference, knowing that the inferences are almost identical. But notice that the sentences here are simplified from the documents that I was showing in the previous slide. And here's what happens when you actually input the complex document into COMET. So COMET predicts inferences. So this complex document has multiple events. So the spent, recovering, and gunshots. And COMET predicts inferences pertaining to any of these events, but indistinguishably. For example, it tells us that Dalton wanted to be safe, which is likely something that happened before he was shot, and wants to get better, which is something that likely happened before he started recovering. And then it also tells us that Dalton wanted to go to the hospital, which happened after he was shot, and to recover from the injury, which is likely happened after he was already in the hospital. And some inferences here don't even make sense. Like, for example, it says that someone wanted to go to jail. Who wants to go to jail? And the others in others one sometimes refers to Dalton himself, like wants to get better, and in other times may refer to someone else, like witnesses maybe that want to go to court. So overall, this is not surprising, given that COMET was trained on atomic events, which are just simple sentences with a single predicate. So to deal with this, we developed a model that gets a complex sentence with possibly multiple events, and then marks one of the events as the target event. And then the model generates inferences for this target event, but in the context of the entire sentence. And for the purpose of event coreference, we only focused on two relationships that seemed the most relevant, which were what plausibly happened before the event and what plausibly happened after the event. So for example, the model tells us that, the model tells us that before Dalton was, before Dalton was spent time at a hospital, he was injured during the shooting and he was taken to the hospital. And then after that, he went through surgery, recovered from his injuries, and was put in a recovery ward. Crucially, we couldn't do the same by just splitting a complex sentence into multiple atomic sentences and feeding them separately in COMET, because then the prediction might actually contradict the context. For example, if you just feed into COMET, Brian Dalton was hospitalized, it also predicts that before this he had a heart attack, which contradicts the shooting, or likely contradicts the shooting. So to train this model, we collected around 100 training examples, and then we fine-tuned GPT-3. So it's a very, very small number of examples. Apparently, if you fine-tune GPT-3, you only need a very, very small number of examples. And the model did very well. I don't remember the exact numbers, but we did human evaluation on the generated inferences, and most of them were correct. So how do we use this model for event coreference? So given two mentions, we generate before and after inferences for each one of the mentions. And then for this candidate pair of mentions, we want to represent these inferences as vectors. And so we represent them each of the before and after inferences for each of these mentions as attention weighted vectors, where the attention could be computed in one of two ways. The first one, which is illustrated here, is interest span. That's where every mention attends to its own inferences. The motivation for that is basically to provide additional context that is not already explicitly mentioned in the document. And what we get from that is a single vector for the before inferences and a single vector for the after inferences, which are, oh shit, sorry, there's the fire alarm here for some reason. Okay, I'm gonna quickly go check that. Okay, I think it stopped. I think I'm safe. I'm gonna continue, unless it happens again.
Just we will wait for you. No problem.
No, it just stopped, so I think it's okay. But if it happens again, I'm gonna leave. Okay. Yeah. So as I mentioned, we get a single vector for before and a single vector for after. We concatenate them, and we get this common sense vector for the mention. And then the second way to compute the attention is not illustrated here. That's interspan attention, where each mention attends to the inferences of the other mention. So the idea is basically to emphasize inferences that are relevant to the other mention. And then we incorporate these vectors as an additional vector in the pairwise scorer. So a typical pairwise scorer represents each mention typically by encoding it with a language model, so getting some kind of contextual representation to spent and hospitalized, concatenating these two vectors and feeding them into the classifier. And we modify that by concatenating to the mention representation also the common sense embeddings that we obtain for each mention. So hopefully we could increase the score of coreferring mentions. And we kept the rest of the pipeline unchanged. So we based it on baseline event coreference model. We got a small improvement in performance upon the baseline. The baseline doesn't use any kind of common sense knowledge. We didn't expect a huge improvement because most event mentions in the dataset are actually lexically or contextually similar. We're working on the edge cases, so that's always going to be a small improvement. And we also showed that our temporal common sense inference model performs better than just using comment directly because of the problem of having sentences with multiple events, and also better than using GPT-3 in a few shot setup without fine-tuning it. Here's an illustration of the interspan attention weights for the mention for two sentences, one with the mention drunk and driving and the other one with DUI. So this is looking at the most attended to inferences. So there is some similarity between the inferences for each mention. For example, one that mentions drinking and driving and the other one that mentions drank alcohol. There's also a similarity between drove his car and drove his car on the freeway. And finally, some inferences mentioning that the police took him to jail. And in addition, the inference for the first mention, the inference that the CHP informs his team, who then suspends him from practicing, mentions the team which is not actually mentioned in the first, in the corresponding mention, but it is mentioned in the second sentence for chargers. That's just a way to illustrate that or demonstrate that in which way the inferences help. In the paper, which is not yet published, it's currently under review, we also have an error analysis where we show that some coreferences are still not resolved due to missing knowledge, and also that the model sometimes actually introduces new errors, especially when the inferences are too generic, and then maybe the inferences of two non-coreferring mentions might be too similar. We're already working on an extended version of the inference model to extending it to various comment relations. And we have another future direction where we want to annotate the plausible inferences with conditions and counterfactuals. So these inferences from the model are plausible, but they're uncertain. And so we would like to know what weakens the inference. Like, for example, if we have an event of calling, like John called Mary, the inferences, there's an inference that John had to have a phone to be able to call Mary. And so we can say that this is true unless, and this is a weakener, he maybe used someone else's phone, or maybe they're in the same room and he just called her from across the room. And we also want to know what would strengthen the inference. So for example, he had to have a phone, especially if he was home alone with no one else with a phone around him, or if he didn't actually remember her phone number, but he had her in his contacts in his phone. And finally, we also want to know what might happen if this inference and possibly the event itself was not true. So that's a counterfactual. For example, if John didn't have a phone, maybe he actually emailed her instead of calling. So this is future work. We haven't started it yet. Okay, I'm going to move on to the second project. I'm assuming questions will be all at the end, even though I can pause for questions now. Okay. So the second work I want to...
Oh, okay. So you can continue, please.
Sorry, what?
Sorry, there are no questions in the chat, so you can continue.
Okay. Sure.
And then at the end, maybe we have more questions. Yeah.
Sounds good. Okay. So the second work I want to discuss is about interpreting figurative language. A few years ago, I looked at the ability of language models to detect when a word is used non-literally. Like, for example, in this headline, furious Meghan Markle says she won't fall for Dad's crocodile tears after he claimed she'd be better off if you were dead. So basically, the question I was asking is whether when you feed this into a language model, it knows that this is not actually about crocodiles. So we found that while models were really good at detecting that it's not about crocodiles, they were far less successful at actually representing that non-literal meaning or non-literal word meaningfully. And if you think about it, it makes a lot of sense. It's actually a lot more difficult because it requires understanding this narrative, maybe having some background about the characters, having some social common sense about how people behave and what they feel. So that's a lot harder. So in a recent tackle paper that was led by Tuhin Chakrabarty during his internship at AI2, we studied the ability of language models to interpret figurative language in narratives. We built 2 data sets of figurative language in narratives, focusing on 2 types of figurative language, idioms and similes. I will focus on idioms in this talk, but if you're interested, there are many more results that I'm not going to mention that are in the paper. So we used online lists of idioms, and then we found 5-sentence paragraphs in the Toronto book corpus that contained an idiom from the list. For example, everyone smiles. You should probably tell your parents about the wedding tomorrow, Carmen suggests. What about you? I ask, not thinking that she will be okay. I'll be fine. Since Dominic isn't up for grabs anymore, I figured I'll concentrate on something else, Carmen declares. Here, the idiom is up for grabs, which means available or obtainable. So we asked crowdsourcing workers to suggest one plausible and one implausible continuation to the narrative, an additional sentence, where plausibility depends on correctly interpreting the meaning of the idiom. For example, Carmen will find someone new to be with is plausible, but Carmen will continue to pursue Dominic since he is available is implausible because it contradicts the meaning of the idiom. And then we define two tasks, discriminative and generative. I'm going to focus on the generative task, which I think is more interesting. So in the generative task, the model gets the narrative and is required to generate the next sentence in the narrative. And we have a lot of baselines in the paper. I'm going to focus on the best performing baseline, which was a supervised GPT-2 based model, and as well as the two knowledge-informed models that we developed. So the GPT-2 based model is a standard sequence-to-sequence model. So we feed the 5-sentence narrative as input to the model, starting with everyone smiles and ending with Carmen declares. Represent that with the language model, and then the language model outputs the distribution over the vocabulary for the next word. During inference, we sample from this distribution, and then we feed the generated word back into the model to get the next word until we either reach maximum length or an end of sentence token. And during training, we just trained the model with cross entropy loss to predict the gold standard continuation. So this is a standard text generation setup, and we expect this model to perform well because, well, both because it's trained on the task, but also because GPT-2 already knows a lot about language and about the world from its pre-training. Then we developed two Commonsense knowledge enhanced models that were based on the GPT-2 baseline. And we're also inspired by how non-native English speakers interpret unknown idioms. So this is based on a paper from Language Education, where the author showed non-native English speakers sentences that contained English idioms that they supposedly didn't know before, and asked them to try to interpret the meaning of the idiom while thinking out loud. And then he analyzed the strategies that they were using and found that the most common and most successful strategies were to either try to interpret the meaning of the idiom based on the context or based on the literal meaning of the constituent words. So here's a new narrative. I'm not going to read the narrative, but the idiom here was run the gauntlet. And so we developed two models, one using the literal meaning of the constituents, the other one using the context. Both of them are using Comet. In the literal model, we use a Comet model trained on ConceptNet, which can generate properties of concepts. For example, it tells us that running is used to get exercise and it is, has the property of being found in a gym, and that gauntlet is used as a weapon. We generate multiple such inferences, and then we trained a GPT-2 based model, which works exactly like the previous model, except that now instead of feeding only the narrative, we concatenate it with each one of the inferences separately. So during training, each inference combined with the narrative is a separate instance that is trained to generate the plausible continuation, the gold standard plausible continuation. And during inference, again, we feed the combination of each inference with the narrative separately, but then we predict the distribution over the vocabulary of the current token for each inference separately and sum them before we actually sample the next token. So the idea here is that we're conditioning the generation of on all the inferences. And I was actually surprised by how well it works. I expected this to yield even like ungrammatical text, but it magically works really nicely. Similarly, we also train a context model. For the context model, we used a version of Comet that was trained on the atomic knowledge base. And the idea here was that we wanted to know as much as we could about the context. So we feed the first 4 sentences of the narrative, which are by design all but the sentence, including the idiom. And in this example, it tells us that the narrator sweats from nerves, feels scared, and wants to feel better. And then the context model is trained in the exact same way as the literal model. I'm going to talk about the human evaluation results. Again, the paper also has automatic evaluation, but it's less reliable in generative tasks. So basically, we took the endings generating for a sample of the stories. We took the endings generated by the baseline, the context, and the literal model, and we asked crowdsourcing workers to judge which one is the most plausible. So the context model was preferred most of the time, and this is pretty nice because it was in line with humans, according to the experiments by Cooper. The context strategies was substantially more common and more successful than the second best strategy, which was the literal strategy. Okay, I'm going to move on to the last project. And so the last project is about completing assumed knowledge. So this is work in progress. It is led by my student Sohail, along with Bodhi from UC San Diego and Manish from IIT Delhi, and everyone's supervisors. And it's combination of or follow-up on 2 prior projects, one that was led by myself and another one that was led by Bodhi. So the first project is my self-talk model. In this model was targeting common sense question answering tasks. Here's a made-up example, which is sort of like a Winograd schema example. So in a sentence like, children need to eat more vegetables because they are healthy, the word they syntactically can refer either to the children or the vegetables. But using common sense, we know that this in this sentence it refers to vegetables. So that was one of the Winograd schema challenge was one of the tasks that we addressed in this project. And the way this model worked was instead of just using the language model directly to score the plausibility of each one of the answers, we had an additional step of knowledge discovery. So we used templates of generic information seeking questions, such as what is the definition of or what is the purpose of, that we input into a language model such as GPT-2, and let it generate questions about the given context. For example, what is the purpose of vegetables? What are the properties of being healthy? And what is the definition of healthy? Then we use the same language model to generate the answer for these clarification questions, assuming that the language models capture common sense knowledge from the pre-training step. So for example, it generates something like the definition of healthy is quality of life that is free of diseases. Then taking all these clarifications and incorporating them into the context, and then using a pretty standard proxy of using the language model score to score the plausibility of the different answer choices. So this model achieved small improvements over the baseline that doesn't have this knowledge discovery component. But one of the main problems with this model was that it was just asking about anything. It was not necessarily asking about the knowledge that was actually missing from the context or the knowledge that would actually be useful to know in order to answer the question. Sorry. And the other project we were basing on is a NACL paper from last year from Bodhi, where the goal of this project was actually to generate clarification questions that are both useful and pertaining to missing knowledge. But it was in a very different domain. It was actually on a closed domain of Amazon product descriptions. So given a product like laptop case, they extracted a local schema from the description of the product using open information extraction. So they extract triplets like trolley strap, attaches, object, etc. And this local schema is basically what is known about this product. Then they look at all the products in this category, all the laptop cases in Amazon. They extract the local schema for each one of the products, and the union of that would be the global schema, which is basically what may be known about this type of product. And the missing schema is the difference between the two, which is basically what might be known about laptop cases in general, but is not known about this specific laptop case. So then they train the model to generate clarification questions that focus on the missing schema and also that are useful to the user, even though I'm not going to go into the detail of the usefulness because we didn't actually follow up on that. So our goal was basically to marry these two projects. On the one hand, target open-ended common sense question answering tasks, such as I did in self-talk, but also determine what knowledge is missing, such as the product project, and then generate that knowledge using language models. So this is the overall pipeline of the system, and I will walk you through it with an example. This instance here is from Social IQA. This is a data set about social interactions. So the context is, Tracy's hobby is woodworking. Tracy built things like baby cribs for the poor in their community. The question is, how would you describe Tracy? As blessed, very grateful, or generous? And the answer is generous. So first we compute the local schema, which is everything that we know about this context. And we do this in a similar manner to the products using semantic role labeling to extract atomic events from the context. So for example, and also changing the names to placeholders for generality. So for example, person one's hobby is woodworking. Second, we cluster similar social IQA instances based on context similarity using sentence embeddings. And then we compute the local schema for each context in the cluster, and the global schema would be the union of all of them. So here's an example. The first items in the schema are from the target event, a target context. The last one here is from a different context. Person one went out of the way to buy food for the homeless. So you can see that it is a cluster about giving. The clustering actually works really well because similarity with sentence embeddings works really well. And then the missing schema is the difference between the global and the local schemas. Then taking the missing schema, we use QA-SRL to generate questions about the different arguments in the missing schema. So QA-SRL generates questions about each semantic role and the corresponding answers. So for example, who went out of the way to buy food for the homeless? And then, yeah, the original argument is the answer. We're not actually interested in the answer because we're not interested in the answer in a specific context. We just want to know, we want to use this question to ask a model about, in general, who goes out of the way. So we generate multiple such questions. We call them elaboration questions because we're asking about something that is not actually mentioned in the context. And then we feed these questions, we input these questions into another model. For now, we're using Macau, which is a general purpose question answering model based on T5. We are in the process of replacing it with GPT-3. Excuse me, just a second. So for example, Macau tells us that some kind people go out of the way. And then finally, we feed the elaborations along with the context, question, and answer choices into the question answering component, which is very similar to self-talk. It's just based on predicting the answer that yields the higher language model probability. And what we expect the model in this case to do is that the mention of kind people in the elaboration would somehow cause the language model to favor the correct answer, which is generous, which is a similar word. So far, we're getting a small improvement on most data sets that we tested. This is the development set results because we're still working on it. And the conclusion is that focusing on missing knowledge is slightly better than asking about anything, but we're still getting a very small improvement. So we're currently working on improving various steps in the pipeline. It is a pipeline, so each one of the steps has some, is still suboptimal. There's a lot to improve. Okay, finally, I would like to discuss some open problems in common sense reasoning and in NLP in general that need to be addressed for common sense models to actually be more useful for NLP tasks. So the models that I presented today need common sense knowledge to use and reason about. In the past, it was common to either collect such knowledge from people or to extract it automatically from text. And the first approach is not really scalable because it's impossible to manually enumerate all the common sense knowledge in the world, and it is costly and time consuming to try. And the second approach works, but suffers from reporting bias. That is, people speak more about the exceptional than about the obvious because everybody knows the obvious. And then this is reflected in text corpora. For example, by looking at corpus frequencies, you might learn that people murder more than they breathe. A more recent approach is to extract such knowledge from pre-trained language models. And finally, some of the methods that I presented today were based on Comet, which really nicely combines human-curated knowledge with language model pre-training. Language models do capture a lot of word knowledge. Here's a handful of examples, actually outdated examples. There are many new papers that show that. Like, for example, they know where Dante was born, which animals have claws, what is the purpose of an internship, etc. Unfortunately, at the same time, they're not sensitive enough to negation, so they can generate incorrect facts such as birds can't fly. And similarly, because of their training objective, they confuse similar but mutually exclusive concepts that appeared in the same context, such as color names. They also don't really differentiate constant facts, such as zebras are black and white, from contingent facts, such as the color of my shirt, which is coincidentally also black and white today. And finally, they don't completely overcome reporting bias. So, for example, I inputted the men turned on the faucet as a result into GPT-2, and it generated the men's blood was sprayed everywhere. And for the same reason, these models are not really great at determining what is not plausible because they're only trained on text of what is plausible, what does happen in the world. If we want to keep relying on text representations or these kind of models to provide the kind of word knowledge that we need for NLP tasks, then the way forward would be, rather than learning it only from text, to learning from additional modalities such as images and videos. They provide complementary knowledge that is unlikely to be described in text. For example, looking through enough class photos, you might learn that the kids in the front row are typically sitting. There's also work showing that predicting colors is improved by incorporating visual features, which is really nice. But we need to be cautious about learning other types of reporting bias from other modalities. For example, we might learn from the movies that people typically hang up the phone without saying goodbye. Even though I have to say I've been using this example now for about a year and a half, and I heard from some people who have teenage kids that kids these days don't actually, they do actually hang up the phone without saying goodbye. So this might be an outdated example. Okay, finally, one aspect of common sense that I didn't touch in this talk is that it's often not universal, but instead culture dependent. And this is something to consider both when you choose the language that you want to learn common sense from, or the collection of images to learn from. So for example, a text in Chinese and a text in English discussing breakfast might talk about different foods, like pancakes in English and noodles in Chinese. And an image of a Western wedding will be different from an image of an Indian wedding. So it's not universal common sense that wedding dresses are white. And some people are starting to think about these things, so that's great. Okay, to recap, I showed that common sense knowledge is useful for interpreting figurative language, resolving long-tail event coreferences, and reasoning about underspecified texts. In another work that I didn't discuss, we also improved visual question answering by generating concept-centric inferences from Comet for the question. So for example, why do they have umbrellas? So Comet generates inferences such as umbrellas protect from the sun and umbrellas protect from the rain. And then we select the most relevant inferences and embed them into the model, helping the performance of the model. But we can get more benefit from common sense models by improving the underlying representation to capture knowledge more accurately, and by mining common sense knowledge from additional modalities such as images and videos to cover facts that are not often discussed in text. Thank you, and I'm happy to answer questions.
Okay, thank you very much. Very interesting talk. Yeah, thank you. And I hope that there are questions from the audience. And if not, I have. So no problem. So we have still some time. Thanks also for being so fitting into the time we had. And let's see if people have questions and want to make questions by the chat, or maybe also participating. Just unmute your microphone, and you can also say. If not, I will start with you. I don't know, Eneko. Eneko wants to make a question. We can hear you. We cannot hear you. No. Sorry. Well, I think we lost an echo. So I have a question for you. Well, question, maybe it's a comment, I don't know. We see that how common sense affects how our programs and machinery are understanding text. So and how difficult is that? And also how language models can improve a little bit the task. But this is a little bit, because even though large language models like, I don't know, P5 you mentioned, or GPT-3 or GPT-2, whatever, so they read a lot. So they have a lot of knowledge. They encode a lot of knowledge, but it's still our improving on this particular task, which are really difficult, like the event coreference or the ones that use the figurative language, etc. So these tasks are very difficult, but our super big language models only provides a little bit of improvement, not large amount of improvement. So the thing is that this still we have room for improving the language models, or we are not using properly the language models we have?
That's a good question. I think that part of the problem is that sometimes you need to, in most cases where you have some instance that requires making some elaborate inference to get to the correct answer, you need to both be able to retrieve or generate the relevant knowledge, as well as somehow combine it together with some kind of a reasoning process to get to the correct conclusion. And I guess there are some tasks or some papers that do it explicitly, but in most cases, I think it's a combination of both, actually, because I think that even when we have, in the common sense reasoning area, there's a lot of neurosymbolic work, but it's pretty shallow neurosymbolic work. It's like we take a neural model and we retrieve some external knowledge, either from a knowledge base or from a knowledge model like Comet, and then we immediately embed it and just put it as like additional input to the model. but we could think of doing something more sophisticated, like actually like defining some reasoning, some way to reason about this knowledge in a more like logical rather than, or like deductive way, rather than just like embedding that knowledge and hoping that the network can learn how to use it. So it's definitely both, like the lack of relevant knowledge, or the like not selecting the most relevant knowledge, the inefficiency of the way that we select the knowledge, and also the way that we embed it into the network. I think there's still a lot of room for improvement. But I also think that with all the advantages of language models, eventually, like you're embedding something, you lose some accuracy. Like you do increase the generalization ability, but that's always at the price of like representing things a bit less accurately. So you always have the risk that it's going to ignore negation, or embed mutually exclusive concepts in proximity in the embedding space. So yeah, I'm not sure if that's something that could actually be addressed within the paradigm of language models, or maybe we actually need a completely new paradigm for that.
Okay, thanks. I think now Eneko is back, so I think maybe he can, if he had a question.
Sorry, can you hear me?
Yep, perfectly.
Okay, sorry about that. Thanks, Beret. It was a great talk. I love this topic and your work. I have a general question. I think it's maybe more than a question. Is to follow with a discussion with what you just mentioned about using language models, because I think that because of the huge amount of common sense which is already learned by language models and also multimodal models, in the last few years we are seeing a lot of work where we are trying to pull out this knowledge or use this knowledge, this common sense, to do the tasks that we just mentioned. But I wonder how you envision common sense, so the implementation of common sense in the next few years. Do you think this is one way to go for sure, but this is something that we need to keep doing? I mean, use larger, more powerful language models and multimodal models and pull the knowledge, the common sense from them? Or do you think, as some of the works that you show, that we also need some common sense encoded apart from the language models, and clever methods to combine the common sense, which is partly in the language models and partly in, say, the templates or the rules or whatever structural representation you have about the task at hand?
Yeah, I think the hybrid approach is probably the most promising one currently. And one evidence for that is how well Comet performs, because it's first of all, it's a lot more, because it was trained on a knowledge base, and it's a lot more structured. It's not just open-ended knowledge. You generate knowledge along several dimensions or like relations from the knowledge base. And also it was trained on a lot of data, so it only uses, I think the language model pre-training only contributes to generalizing maybe across paraphrases or some like generalizing similar events, but it is usually pretty accurate. It's not perfect because it's still a model, but it's pretty accurate. So I think that's a really good example for a hybrid approach, where you take a very large scale knowledge base and then you fine tune a language model on that. And I think, in general, when choosing which sources of knowledge to use to retrieve or generate knowledge for a particular task, I think, always like a hybrid approach would be the best. Like you could extract knowledge from language models and from a knowledge base, and somehow encode your domain knowledge into the system, maybe using something like templates, or designing the network architecture that would not be just like a simple sequence to sequence task, but also maybe incorporating some kind of like I don't know, different way to different decision-making methods based on our intuition about how humans solve these tasks. And so I think, yeah, probably like the most promising approach would be some hybrid approach of all of these. And also something that I haven't personally done, but I think trying to get inspiration from cognitive science about how people process these kind of tasks or process language in general could be useful. We don't have to have models that behave exactly like humans, but we can definitely get some inspiration.
Okay, thanks.
Great. If there is any further questions from the audience, if not, I already have, so no problem.
I think there is a hand raised.
Hand raised. Okay.
Hi, Barry. I'm Fang Jun, and I'm from University of Leeds. And thanks for your talk. It's very interesting topic, and you gave good explanations of your three aspects of research. And one thing I'm interested is that I remember in one page of your presentation, you mentioned attention score analysis, and that's the question answering task, right? And is that task a multiple choice task? For example, you have 4 choices and you need to select the right one.
You mean this one?
No, there is one page called attention scores analysis.
Yeah,
I remember it's in part 2.
Yeah.
Yeah,
this one.
Yeah, this attention score. I see that you get some attention scores for before, for example, before drunk driving, there are 4 choices. So is that a multiple choice task?
No, this is the event coreference task. So the goal here is to represent additional common sense knowledge about each one of the sentences. And we generated multiple inferences, and then we weight them when we create the vectors. It's this one. So basically generating before inferences and after inferences for each document, each mention, and then creating an aggregated vector, common sense vector for each one of the mentions. And in this example, the attention scores were based on basically it's learned, so it's based on similarity to the other mention. So sorry, to the same mention. This is the interest. Yeah.
Thanks.
So for each mention, like drunken driving, the most attended to inferences would be the ones that are similar, that are helpful in the context of the task. So for example, Jamal is drinking and driving would be the most similar one. And then the idea, what I wanted to show in this slide basically is that, okay, these are the inferences that are highlighted by the model. And now I want to show why it actually helps. So it helps because there's some similarity between the inferences across the 2 mentions. It helps determining that these 2 mentions are coreferring.
They're quite clear. Thank you.
Yeah, sure.
Okay, thanks.
I have another problem that apart from those attention scores, or because for language models, usually what way usually do for a result explanation that we use some scores for evaluation. Apart from that, do you think there any other ways to illustrate that those common sense things did work for the language models?
So I'm not sure I understand. Apart from the attention scores, what was the question exactly?
Apart from the attention scores, is there any other ways to show that the common sense things that were imported did work for the language model?
Yeah, so we actually looked at the number of instances that were incorrectly predicted by the baseline and correctly predicted by the model, because the only addition of the model is basically these common sense embeddings. in the pairwise score. So we had a number of these. It's not a huge number, but the only reason is because this data set doesn't actually, most of the instances don't actually require common sense. And that's probably the case in most NLP tasks. Most instances are straightforward and don't require any kind of additional knowledge. But we do show that for a subset of the instances, our model manages to correctly predict them with the knowledge, but not without the knowledge. So that's one way to show that in general it works.
There's some analysis of the instances. I got that. Thank you.
Yeah.
Okay, thanks. Any further question? Any comment? Somebody wants to?
Can you hear me?
Yeah.
Yep.
Yeah, thanks for the talk. I have a question about the last project that you showed. I want to ask that, do you think that asking follow-up questions would cover for the missing data, and that would perhaps give better performance compared to the computing missing scheme that you mentioned?
How much do I think it might help asking clarification questions?
Yeah, asking follow-up questions to cover this missing data, because I'm guessing that you're asking nested questions to basically get the concept, get the context for knowledge discovery part. And if you follow up those questions, would it yield to better results, perhaps?
Yes, that's a good question. We didn't actually get to that point in this project yet, but that's something that I was wondering when I was working on the self-talk model. I think I did try at some point. No, I didn't try follow-up questions. I did try to generate to incorporate multiple questions. Yeah, sorry. So we do generate, in this model and in self-talk model, we do generate multiple questions. And then we do have a selection process that I didn't mention in this pipeline, that we end up incorporating the 5 best elaborations based on similarity. But I agree that follow-up questions might definitely help in the cases where you need multi-hop reasoning to solve the question. So I think it's actually crucial. We haven't tried it yet with something that we do need to try. My concern about that would be that you gradually lose relevance. You get further and further away. And also, like, it's a propagating error. So if you generated an answer for the first elaboration question that is incorrect, and then you elaborate on that by asking more questions, you can get more errors. So that was something I was concerned about. And also the runtime, it just gets more complicated if you do this like sequentially. But I do think it's going to be imperative to solve the multi-hop reasoning instances.
Thank you.
Okay, thank you very much. I think, well, I have a comment, the last comment. I think we are almost at time, so thanks once again. I have one last comment. You didn't mention in your presentation anything about abductive reasoning, which is most of what we are doing when we are processing common sense, is bringing back some knowledge we need at that moment for making a proper inference. And the most plausible or the most relevant knowledge we have for answering properly the task at hand or the question at hand, etc. So at the end is a way of trying to wrap from the language model this particular, the knowledge you want from them. No? We can do prompting, we can do many just generations, we can combine. But what we are trying to do is some kind of abductive reasoning, so trying to get the most appropriate knowledge for this particular problem we have at hand. So, but you didn't mention on purpose. I mean, it was something deliberate, or maybe it was which is beyond the scope. I don't know. I think this is missing somewhere. I don't know.
Yeah, I definitely agree. It was not on purpose. I have worked on abductive reasoning in the past, just not recently, but I do plan to keep working on that. In general, about Well, I did mention in the context of the expansion that we want to do for comment with the counterfactuals and the diffeasible conditions. And in general, I have worked on non-monotonic reasoning, and I want to go back to that because in common sense, like most inferences are just plausible. You don't really know. It's something that might be true, and given additional information might turn out as not true. So yeah, I definitely plan to go back to working on these things, and both developing new reasoning models with abductive and counterfactual and diffeasible reasoning, and also then incorporating them into NLP models. I do have some ideas on how these models, if they perform well, they can actually help downstream tasks.
Thank you very much. It has been really, thanks. I think I also agree, and thanks a lot for your presentation, your talk. It has been nice to think a little bit on different tasks and also on different ways to incorporate common sense. Thanks also for waking up so early for you. I think it's 7:30 when we started, so thank you again for this effort to participate in this webinar, in the seminars. And I think we have a last slide to show for the next webinar, which is going to be on December. So thank you again, Beret. I hope to see you in person soon. I don't know where, but I hope to see you very soon. And thanks a lot, everybody, for participating. And we are going to distribute the new webinar very soon. So thanks a lot, and
thank you very much.
See you soon.
See you. Thank you.